Chapter 13, Section 4, Probabilities of Compound Events. This, to me, in my opinion, is where we really get into the fun stuff of probability. We look at different situations, more real-life applications, and something that might make a little more sense to you rather than just drawing one card or rolling one dice. It gets way more fun when we talk about multiple events, specifically compound events. So we got two really different types of probabilities here in this section. The first one is and or then events, and when I say and or then, I mean like we're going to find the probability of A and or then B. Okay, so we're talking multiple events here. We're going to draw multiple cards. We're going to roll multiple dice. We're going to spin a spinner more than once. We're going to make multiple selections, things like that. Okay, and we'll get into the other type of probability a little bit later, but we're going to start with and or then events. This, the and then, that's not a vocabulary term, but that's just kind of where we're starting. Okay, so if our events are independent, and we've talked about independent before, the way we find the probability of independent events. So let's say we're going to find the probability of A and then B. How we're going to find that is we're going to take the probability of event A happening, and we're going to multiply it by the probability of event B happening. And that's all there is to it. We're going to take the two probabilities and we're going to multiply them together. A lot of times what you're going to hear or what you're going to see when we're talking about independent is the word replacement. Okay, we're going to put the card back. We're going to put the sock back in the drawer. We're going to put the marble back in the bag. We're going to replace what we're drawing from. And that's what makes an event when we're drawing out of a deck of cards or drawing out of a bag of marbles. That's what makes the draws independent. Now, it would be the same thing as if we had two identical decks of cards or two identical bags of marbles, and then we're finding the probability of each one. The key word here with independent events is replacement. Okay, so if we put something back, then we're talking about independent events, and all we need to do is find the individual probabilities of each event and multiply them together. So let's jump into a couple of examples here. Using a standard deck of cards, find each probability. So number one, we're going to select a face card, replace it, and then draw an ace. So that's the key word there, replacing it, just like here in number two. We're going to get there in a second. So selecting a face card, replacing it, then drawing an ace. So the probability that we get a face card, let's see, there are 12 face cards in the deck. We got the Jack, Queen, and King of each suit. So there are 12 face cards out of the 52 total. If we want to simplify this right now, we can. This would be 3 over 13, which makes sense. 3 faces out of the 13 cards in each suit. The probability that we get an ace. Okay, so we put the card back, and now we're gonna draw the one card, and we're looking for the probability that we get an ace. There are 4 aces in the deck out of the 52 cards. 4 over 52 simplifies down into 1 over 13. And once we get these two numbers, all we need to do is multiply them. This becomes 3/13 times 1/13, and we multiply straight across. 3 times 1 is 3. 13 times 13 is 169. And I'm going to leave my answers as fractions for the most part in this video, just because we're going to be working with fractions a lot, and it's going to be the easiest way to write our answers. So 3 over 169. So if we were to do this experiment where we draw 2 cards, we put the first card back, if we did it 169 times, in theory, we should get a face card and then an ace 3 times. That's what our probability tells us. Question number 2 says selecting a spade, replacing it, then drawing a face card. Again, we're replacing, so we are talking independent probabilities or independent events. We need to find the probability that we get a spade. Okay, so the probability that we get a spade, there are 13 spades in the deck out of the 52 cards. If you want to jump right into 1 over 4, I'm okay with that. That totally makes sense to me. You don't necessarily have to show me 13 out of 52 to start with. We've replaced the card now after we drew that first one. We're going to put it back. Now we're looking for the probability that we draw a face card. We've already done that. We saw that right up there in the first example. So I'm just going to go right to the simplified fraction 3 over 13. And then again, since we've replaced, we're talking independent events, we're just going to take the two probabilities and multiply them together. 1/4 times 3/13. We multiply straight across. 1 over 3 is 3. 4 times 13 is 52. So 3 over 52 is our probability for drawing a spade, replacing it, and then drawing a face card. If the events are dependent, meaning the second event is dependent upon the result of the first one, then our formula is slightly different, kind of. We have to think about the problem in a slightly different way. So probability of A and / then B, if we want A to happen and then B to happen, or A then B happens, the formula is this. We take the probability of event A, just like before, times, just like before, probability. Now this is where it gets different. The notation looks a little bit different. It's B with a vertical line and then A. And how you say this is B given A. What this really means is that we have to assume that A occurred. We're finding the probability of B with the assumption that A happened. Because if A didn't happen, then our probability is going to be 0. There's no way we could get A then B if A didn't happen. So we're going to find the probability of event B happening, whatever it might be, with the assumption that A already did happen. Okay? The key word here with dependent events is no replacement. Okay? We're not going to put the card back. We're not going to put the sock back in the drawer. We're not going to put the marble back in the bag. Okay, so there are our fractions, our probabilities change for that second event because our sample size or our sample space is just slightly different than the first time. So let's try an example here. Huey has a bag that contains 4 red, 6 green, and 3 brown candies. He randomly chooses 3 candies from the bag. Number 1, determine if the events are independent or dependent. Now, this question does not say that he puts the candies back in the bag. We're just going to draw one after the next. We're not going to replace. And since it does not say anything about replacement, I would say this is a dependent situation. These events are dependent because we can say there's no replacement. It doesn't say anything about he's going to put the candies back in the bag, so we have to assume that he's not going to. So this makes it a dependent situation. Question number 2 then says, what's the probability he will choose all 3 brown candies? Okay, so what this really means, if we're looking for the probability of all 3 brown, I should have done this in brown just to be, very appropriate. We don't have to though. What we're really looking for is the probability that we get a brown, and then a brown with our second draw, and then a third brown with our third draw. Okay, so let's try to figure out what each probability is individually. Then we know, according to this formula, that we have to multiply them together. Now this gives us 2, but we can certainly add more than 2 if there's more than 2 events, like there is here in this example where we're drawing 3 candies. Okay, so the first event, we're drawing a brown candy. So the first event, we're going first draw. The probability that we get a brown is what? Well, we know there are, let's see, 4 plus 6 is 10, plus 3 is 13. There are 3 brown candies out of the 13 candies in the bag, so we can say 3 over 13. That's pretty straightforward. For the second draw, here, we're looking for a probability that we get brown, given that we drew a brown already. Okay, so we have to assume that the first candy we drew was a brown. And we know that we drew 1 candy because this is the second draw, which means there are 12 candies left in the bag. If we assume that the first candy we drew was brown, how many brown candies are left in the bag? And the answer to that then is 12. If you want to simplify this down into 1/6, feel free. Okay, so the probability that we get a brown with the assumption that the first candy was a brown is now 1/6. We have to do this a third time because we're drawing 3 candies. So third draw, we're going to look for the probability that we got a brown, or the probability that we get a brown with the assumption that we've already got 2 browns. Okay, so let's see, we've drawn 2 candies, which means in the bag there are now 11 candies left. We have to assume, in order for this to work, we have to assume that the first 2 candies were brown. So if we take out the first 2 brown candies, that leaves us with 1 brown candy left in this bag. And 1/11 is as simplified as it gets. So what this all means then, when we go to write our final answer, the probability that we get 3 brown candies, and notice I'm doing this in brown now, 3 brown candies is going to be equal to 3/13 times 1/6 times 1/11. Now, if you made this 2/12, you would not get a simplified answer. Remember, your calculator can simplify that. That's just math, enter, enter. But if you write it out with simplified numbers or simplified fractions right away, you should get an answer that is simplified. This one's not going to be simplified right off the top because I can see that the 3 and the 6 could cancel out. So if I do that right away, make that a 1 and make this a 2, now it should be simplified because I've got 1s across the top. When we do this, 1 times 1 times 1, that's pretty easy, that's 1. 13 times 2 times 11, 26 times 11 is going to be 286. So you have a 1 in 286 chance of selecting all 3 brown candies. So theoretically, this says that if we were to do this experiment 286 times where we draw 3 candies and then put them back and start over, we should get all 3 brown one time. Does that mean that's going to happen? No, we might get it twice, we might get it 4 times, we might get it 10 times, we don't know. But if we did this experiment 286 times, we should have all 3 browns just once. All right, let's try another one here. Refer to the previous card example. So we're talking about these where we select a face card, replace it, then draw an ace. But now the keyword here, do not replace. Okay, so now we're talking about dependent events. So probability of a face card and then an ace, just like the first example on the last one. So probability of a face card, this is our first event. This is not going to change. The probability of a face is still 3 over 13. Okay, we're going to go right to the simplified fraction. Now, the second part is a little bit different. The probability of an ace given that the first card was a face. Now, since we haven't put the card back, that means our deck is now a little bit smaller. We now have 51 cards in our deck for the second draw. We did not draw a face card the first time, or we did draw a face card in the first time, which means we still have 4 aces left in the deck. So my fraction here, the probability of getting an ace with the assumption that the first card was a face card is going to be 4 over 51. And just like the last example now, once we have our conditional probability, or once we have our dependent probabilities figured out, all we need to do is multiply these fractions together. We can say 3 over 13 times 4 over 51. This is going to be 12 over 663. This can be simplified down into 3 over 221. And I just realized I have an error. That's not going to be 3 over 221. That's going to be 4 over 221 because I'm dividing both of these by 3. 663 divided by 3 gives me 221. 12 divided by 3 is 4. All right, let's try another one here. Number 2, probability we get a spade and then another spade. So now we're going to have to think about a different situation. So the first part, normal. Find the probability that we get a spade. So the probability we get a spade, if you want to go right to 1/4, I'm good with that. There's 13 spades out of the 52 cards. 13 over 52 is 1/4. Or you can think 4 suits, one of them is spades. All right, second part, probability that we get a spade with the assumption that the first card was a spade. Now, first card was a spade. We've drawn a card. We have not replaced it, which means our denominator here in the second fraction is still going to be 51. We've changed the number of possible outcomes to 51. Now, we assume that the first card was a spade, which means there are now 12 spades left in the deck for us to pick from. Okay, so it's not going to be 13 out of 52. It's not going to be 1/4. It's now 12 over 51. Okay, so what this means when we multiply these together, because now we've got our two fractions, it's still the same process, 1/4 times 12 over 51. All we need to do is multiply straight across and simplify it, or we can simplify it first. These are both divisible by 4, so that's a 1, that's a 3, and 1 times 3 is 3, 1 times 51 is 51, and this is our final answer, just like it is up there. So I want you to kind of realize there, so this one was exactly the same as the first one, except our probabilities were different. So in the previous example, a face then an ace gave us 3 out of 169, but if we don't replace it, now it's 4 over 221. So our chances of getting a face card and then an ace, if we do not replace the first card, go down pretty significantly. All right, let's move on to OR events. We talked about and/then. Now let's move to OR events. Now, OR events involve a single trial, meaning we're drawing one card, we're spinning a spinner once, we're rolling one dice. Well, I guess plural, singular of dice is die. It's a number cube. The book usually refers it to a number cube because technically it is, but usually we call it a die. Okay, so when we're talking a single trial, we have two different types of events. We have mutually exclusive events, or we have inclusive events. Mutually exclusive events are events that cannot happen at the same time. For example, we can't roll a 2 and roll a 5 with one roll. Okay, it's not possible. Just like if we're drawing one card, and the key here is we're drawing one card, spinning the spinner once, roll one die. We can't have a 7 and a queen with one card. There's no 7 of queens or queen of 7s. It's not possible. Inclusive events means they can happen at the same time. For example, rolling an even or a 4. That's possible. We can get an even and a 4 because 4 is even. Just like a spade or a face card, there are 3 face cards that are spades. We got the jack of spades, the queen of spades, and the king of spades. It's possible to have a spade and a face. So if the events are either mutually exclusive, meaning they can't happen at the same time, or they are inclusive, meaning they can. The formula, whether it's exclusive or inclusive, is really pretty much the same. The probability of A or B, and you'll be able to tell the difference between and/then or just by this word in between. It's either A or B, or then it's going to be then or and. Okay, so that's going to be the difference. The probability of A or B is equal to the probability of A plus, this time we're going to add the two probabilities, the probability of B minus the probability of, and the book usually, and most publications use A and B. I don't like A and B because then I think we get confused going back to, some of this where we start multiplying things again, and that really doesn't make a whole lot of sense to me. So I like the word both, just because both have to happen. I think that makes sense. If the events are mutually exclusive, we can ignore this part right here. Okay, we can say only for inclusive events. Okay, so only for inclusive events are we going to have this third part, because the inclusive events, this part that I've got boxed in here in blue kind of takes, or not kind of, it does take into account the events that you would have double counted if you were going to count all the possible outcomes. Okay, so if we're talking about the spaces or the spades, we would have counted the Jack of Spades, King of Spades, and Queen of Spades twice. So this kind of takes out the double counting. And if they're mutually exclusive, we just need to add the two together. If they're inclusive, then we have to take out the probability that it's both. And I've got a couple of examples here to kind of show you the difference. All right, in a particular group of hospital patients, the probability of having high blood pressure is 3/8. The probability of having arteriosclerosis is 5/12. And I'm not sure what happened here. This is supposed to be the word and the probability of having both is 1/4. Number one, determine if the events are mutually exclusive or inclusive. Well, it says probability of having both is 1/4. If it was 0, then it would be mutually exclusive. But since you can have both, I would say this is an inclusive event. This is an inclusive situation. Inclusive. Because patients can have both. Patients can have both. Okay, so it's an inclusive situation. Question number 2, what's the probability that a randomly selected patient has high blood pressure or arteriosclerosis? All right, so we're talking or probability. So we're going to add the two probabilities, the individual ones together. So blood pressure is 3/8. So let's see, probability of high blood pressure, HBP, or I'm going to abbreviate arteriosclerosis as AS, is equal to the probability of high blood pressure plus the probability of arteriosclerosis minus the probability that the patient has both. And all we're going to do is fill in some spaces. The probability that we have high blood pressure is 3/8. The probability of arteriosclerosis, that says it right there, it's 5/12. And the probability that we have both is right there. That's going to be 1/4. Now you can use your calculator to do this for you. If you want to go ahead and make this into common denominators, feel free. But I think most of you are going to go right to the calculator, and I don't blame you. The probability that a randomly selected patient has high blood pressure or arteriosclerosis is going to be 13 out of 24. So there's a quick basic example of how to use or probability. I've got one more here for you, a little bit different, a little more complex, but important nonetheless. So there are 5 students and 4 teachers on the school publications committee. A group of 5 members is being selected at random to attend a workshop on school newspapers. What's the probability that the group attending the workshop will have at least 3 students? Now, key phrase here is at least. So what this means, and I'm going to make this in quotes, at least 3 really means we could have 3 or 4 or 5. Okay? Now, the question then I think becomes, are we going to add the probabilities together, or are we going to multiply? Because we've talked about both. I would say we are going to add these probabilities together, because we can't have 3 and 4 students at the same time going to this workshop. It's either one or the other. We're taking one group of people. It's either 3 students or 4 students or 5 students. Okay? So I don't think we need to do any multiplying. We're just going to do some adding in terms of probabilities. We might need to do some multiplying prior to adding the probabilities, because we need to figure out what the probabilities are, but we're not going to be multiplying any specific probabilities together. So let's try to figure this out. So if we're going to take 3 students, and how many adults is that going to mean are in our group? We know we're taking 5 people total. We've defined that we're going to take 3 students. That means we're going to take 2 adults or 2 teachers. Okay? If we're taking 3 students, We have 5 to pick from. Again, this is kind of goes back to permutations and combinations, specifically combinations, because the order in which somebody's chosen doesn't matter. As long as you're chosen, you're going. So this, to me, this is going to be 5C3 for the students, times, because the students we pick doesn't affect the teachers we pick. We have 4 teachers on the committee. We need to take 2 of them. Okay, so if we're taking 3 students and 2 adults, it's going to be 5C3 times 4C2. And when you do that in your calculator, you're going to get 60 possible groupings of 3 students and 2 adults. Okay, so there's the 3 student possibility. Now, what about 4 students? If we take 4 students and 1 adult, we're going to modify the prior formula just a little bit. We're going to take 5C, and this time we're going to do 4 because we're taking 4 students, times we got 4 adults and we're choosing 1 of them. If you do this one in your calculator, you are going to get 20 possible combinations. And the last one we need to do is 5. So if we take 5 students and 0 adults, we're going to have 5C5 because we're taking all 5 students, times 4C0 because we got 4 adults and we're choosing none of them. The number of ways that this can happen is 1 because you're taking all of the students and none of the adults. There's only one way to do that. So that's going to be, these are going to be key pieces of information. Now, we need to figure out how many possible groupings of people we could take if there weren't distinctions between students and teachers. So what we need to do first is we need to figure out what our denominators are going to be, because these are going to be our numerators. Okay, these are going to be the possible successful outcomes of our problem. The denominator, the sample space, is going to be this. We got 9 people total. We got 9 people in our committee. We need to choose 5 of them for our the group going to the workshop. We're not defining the number of students versus the number of adults. So we're just going to do 9C5. When you do this one in your calculator, you are going to get 126. So there are 126 different ways to pick 5 people out of this group of 9 on the committee to go to this workshop. But we're kind of looking at the specific situation where we have 3 adults, or 3 students, 4 students, or 5 students. And since we're going to add these together, this is the denominator for all 3 of these fractions. So we're going to do this. We're going to do probability. Whoops, I'll go back to the pen. Probability that we have at least 3 students is going to be equal to the probability that it is 3 plus the probability it is 4 plus the probability it is 5. And what that looks like, probability of 3, let's see, 3 students, 2 adults, there were 60 different ways, so we'd have 60 over 126, plus probability of 4. There were 20 ways to do 4 students, so 20 over 126, plus the probability, the ways we can do 5, that's just one way to do 5 students out of 126. Now, I highly doubt that that would happen. They're not going to send 5 kids to a workshop without any adult supervision, but in theory, it would be possible to select all 5 students to be part of this workshop. All we need to do is add those 3 numerators together because our denominators are the same. 60 plus 20 is 80, plus 1 more gives us 81 over 126. This can be simplified down into 9 over 14. This is our final answer. It's a 9 in 14 chance that there would be at least 3 students in this committee going to the workshop.